Hello everyone, in this video we're going to explore depth first search algorithm, or DFS for short. What is DFS exactly? Well, it's a search algorithm that prioritizes exploring depth in a search tree. It works by expanding nodes and following one path as far as possible until it hits a dead end, before backtracking to explore new paths. Let's see how it works in action. Suppose we have a search tree. Each node is labeled by a number, like 10, 20, 30, and so on. This number serves for identification purposes only, and it has no significance to the actual search logic or mathematical properties of the tree. It's just a label. This tree is called the binary tree because each node is expanded into two children nodes. The branching factor of this tree is equal to 2. Our algorithm first starts by taking the root node, which is labeled as 10. The root node is then expanded into its children nodes, which are 20 and 30. DFS decides on an expansion order, for instance, left to right, and then it sticks with it until the end. So, we choose to expand the first child, 20. Expanding 20 leads us to its own children nodes, 40 and 50. Again, following our order, we choose to expand 40. Notice that when we expand a node, we check for the children nodes that are unvisited. If we were not tracking visited nodes, a graph with cycles could cause the algorithm to get stuck in an endless loop. Therefore, in practice, a DFS implementation nearly always includes a check to disregard nodes that have been already visited. Let's continue. We expand 80. Now we realize that 80 has no unvisited children. We have hit the bottom of the branch. At this point, we need to backtrack. We move back up to the nearest node that still has unvisited branches. That was the node 40. We look at its next child 90. We expand 90. If 90 has also no unvisited children, we backtrack again all the way up to 20, and then explore its other child 50, and so on. We continue this sequence until we have either found a goal or covered the entire search tree. Let's have a look at the core concept in the code. The function here takes a node, such as the root, and immediately mark it as visited. After that, it iterates over every neighboring node, which are the children in the search tree structure. For each neighbor, we first check to make sure the node is unvisited. If it is unvisited, we simply call the exact same function on that neighbor. This is a classic example of a recursive function, where the function calls itself. This recursion concept is what allows DFS to automatically dive into a single path as deep as possible. Finally, let's discuss the performance of DFS using the 4 metrics that we have talked about in the last video. First one is completeness. Is DFS considered a complete algorithm? Completeness means it is guaranteed to find a solution if one exists. If we consider a finite search tree, the algorithm is complete, as it will cover every node in the search tree. However, if we consider an infinite search space, the algorithm is not complete. It could pick a path and dive deep into it without ever reaching a solution, even if the solution was located just one step off the main path near the root. Second is optimality. Is DFS cost optimal? Optimality means is the first solution found guaranteed to be the lowest cost path. This algorithm simply follows the depth first and doesn't regard the cost or weight of the edges or the length of the path it takes. Therefore, DFS is not cost optimal. It might find a deep long solution before finding a shallow, short, and much better one. Third metric is time complexity. Time complexity measures the maximum number of nodes DFS might visit. For a tree with a branching factor b, which is the maximum number of children per node, and the maximum depth m, the time complexity is b raised to the power of m. As in the worst case, the algorithm might have to explore every single node up to the maximum depth. So you multiply the branching factor by itself m number of times, where m is the maximum depth of the tree. That's how you get b to the power of m. Fourth is space complexity. Space complexity measures the maximum number of nodes the algorithm needs to store in memory. This is where DFS really shines because it only explores one path at a time. It only needs to store the nodes on the current path, from the root node to the deepest node being explored. Therefore, the space complexity is only proportional to the depth of the tree, which is b times m.